magnetic field due to segment 3. You might notice that that looks an awful lot like segment 1, so we'll use some of the same ideas. Segment 3 has current flowing this way, point P is right here. Magnetic field B3 is mu naught times 4 pi times I times ds cross r hat over r squared. ds is a little bit of the path along the wire. R is from the wire to the point. And then our r hat, of course, is in the direction of r. So for this one, similar to the first one, we have ds and r hat anti-parallel. So if we did the magnitude of ds cross r hat, we'd have ds times the magnitude of r hat times sine of 180, and we'd still get 0. So ds and r hat are anti-parallel. The magnetic field due to 3 is 0. Okay, let's also do 4. So our magnetic field due to segment 4, let's draw segment 4 first. So that looks a lot like segment 2 with a couple of key differences. For this segment, the diameter, the radius is bigger, so this is 2 centimeters instead of 1 the way it was previously, and the current goes in the opposite direction. So the current on this guy comes around this way. So when we pick our ds, it's a little bit in that direction. Our r vector comes from here to here. So the r vector looks like this. In this one, the magnitude of r was written down as d. R hat, again, same deal as before. R hat is a unit vector that points with r, and point P is here. Let's write down that magnetic field 4 is the integral of mu naught over 4 pi times I ds cross r hat over r squared. Now, let's not reinvent the wheel here. Let's use some of our previous results. So we'll just show this part right here. First thing we'll write down is that the magnitude of B4 is the integral of mu naught I over 4 pi, magnitude of ds cross r hat over r squared. ds cross r hat is magnitude of ds, magnitude of r times sine of the angle between them. So magnitude of r hat is 1, sine of 90 is still 1. So that's mu naught I over 4 pi times ds. We'll take our constants out front of the integral, just like we did before. Oh, I dropped my r squared. Let's put that back in there. So we've got mu naught I over 4 pi r squared times the integral of ds. Again, the integral of ds, we're going halfway around the circle, so the integral of ds is that total distance, which is half a circumference. So we get mu naught I over, oops, pi cancels, r cancels, mu naught I over 4r. So let's remember that r was written as d in the image of the problem. So B4 is mu naught I over 4 times d. So taking care of that notation. We also want to get the direction. If we use our right-hand rule where we're curling, our thumb goes with current, our curled fingers come out of the page. Or we can do ds cross r hat gives b out of the page. Either way is fine, they both give the answer. So the magnetic field is out of the page, and in Cartesian coordinates that would be a k hat or positive z, and we can put in brackets out of page. Okay, the last part's pretty straightforward. Total magnetic field would be the addition of those vectors. So B1 was 0, B2 was mu naught times I over 4r k hat, and that guy was negative, plus B3 is 0, plus B4 we can make that look a little bit nicer. We get mu naught I over 4 times minus 1 over r plus 1 over d times k hat. Okay, so there's our expression. Let's get our numbers that we're going to put in there. So what we know is mu naught equals 4 pi times 10 to the minus 7 Teslas meters over amps. I is the current that was given as 5 amps. R is the distance to the smaller circle, which is 1 centimeter or 0.01 meters. D is our distance to the outer perimeter, that was 2 centimeters or 0.02 meters. Put all those numbers in our equation and we can plug and chug to get our answer for the net magnetic field, which is minus 7.85 times 10 to the minus 5 Teslas k hat. So our net magnetic field is into the page.